In our last class, we have discussed about parameters of the flexible pavement design. In this class, we design one flexible pavement. In the design of the flexible pavements, there are different methods. Okay, so basically in India, we follow IRC method or Indian Road Congress method. So basically that IRC code is IRC 37. So based on this IRC code, the design of the flexible pavement is based on the CBR value or California bearing ratio values. So based on these CBR values, we will design what is the total thickness of the flexible pavement. In this way, let us solve one example. So for this, see here, it is given that severe value of subgrade soil is 5%. Calculate total thickness of the pavement using your question would be that second one. Design chart recommended by IRC. So that is your question. So from this question, you have to find out what is the total thickness of the pavement. And another thing is given that you have to design the pavement for a medium light traffic. Okay, you have to design for the medium light traffic conditions. So how you are going to design that pavement? So basically that is very simple task. So just you have to find out that particular your chart from the IRC 37 code. So if we going to the chart, basically this is the chart. Okay, so in the top portion, that is the x-axis, it's defined different severe value, that is the California bearing ratio value, and that values are in percentage values. In the y-axis, that is the depth of the pavement which you have to find out. Okay, depth of the pavement, and these three curves are assigned to find out the traffic conditions. Okay, the first curve is for the traffic for light traffic conditions. Okay, light traffic conditions. The second one is for the medium traffic conditions, and the last one is heavy traffic conditions. So for our case, as it is written as light traffic condition, so we will follow the middle curve. Okay, so in the question it is given as your CPR value is 5%. So that is the 5% severe line. So you have to find out this 5% severe line intersect at which point. So it will be intersecting the medium traffic curve in this point. So then you have to draw one line joining this to the x-axis, and where this line intersect to the x-axis, that is your total thickness of the pavement. So from the curve, it is found out that the total thickness of the pavement is like 38 centimeter. So that is the total thickness of the pavement, and that is the design of the flexible pavement. Okay, so again I am discussing this. First, you have to find out the corresponding severe line. So that is your corresponding severe line, and you have to find out at which point it intersect the curve. So this is the point where it intersect the curve. Then again you have to draw a line joining that point to the x-axis, and at the x-axis at which point it intersect, that is your total thickness of the pavement. So from this you can easily find out your total thickness of the pavement is 38 centimeter. Is it clear? So in this example, we have found out what is the severe value. Based on the severe value, what is the total thickness of the pavement. Now let us consider another example from where you have to find out what is the thickness of different layers. As you know, flexible pavements are composed of different layers. So in this example, you have to find out what is the total thickness of the different layers. So in this example, a severe test values are given. So as we have already discussed that severe value is recorded as a load value based on the standard penetration values. So these are the standard penetration value, that is 0, 0.5, 1, 1.5, 2.5, then 3, 3.5, and according to this penetration value, your severe test results are given as load values. So these are the load values. So you have to find out what is the first you have to find out what is the severe value. Here traffic parameters are also given. So first we need to find out what is the severe percentage value. So here area of the plunger diameter is 19.6 centimeter square. So pressure, you can find out the pressure, or you can directly find out the severe value using the standard load values. Okay, so after that you have to draw one curve. So that is the curve. Okay, so in the curve, in the x-axis there would be penetration values, and in the y-axis there would be load values. So based on this load and penetration, you have to draw a curve. You can draw this curve. So after drawing this curve, you can observe that in this portion there is a convexity of the curve. Okay, so if such type of convexity appears, in that case it means that your curve needs some corrections. So how to correct that curve? In that case, you will draw one line joining that convexity points to your x-axis, and at which point that intersect, that would be your new zero line. So basically you are shifting your curve towards this direction to a amount of this portion. Okay, so after that you have to find out what is the severe value of the soil at 2.5 mm penetration. So your severe value would be load at 2.5 mm divided by standard load. Now for the standard load, your standard loading value is 1370 kg. Either you can use that pressure values, or you can use as your load values. So it is found that severe value at 2.5 mm penetration is 4%, and severe value at 5 mm penetration is 3.5%. Now as the severe value at 2.5 mm penetration is more than the severe value of the 5 mm penetration, therefore this result is accepted, and yes, your severe value for the subgrade soil is 4%. Now you have to design different thickness of the pavement section. So before this, you have to find out what is the total number of vehicles at the completion of the your road project, and that is found out using this formula. As you know, here in the question it is given as the traffic survey revealed the present ADT of commercial vehicle as 1200. Annual growth rate of the traffic is found to be 8%. The pavement construction be completed in 3 years after the last traffic count. Okay, so these data are given. So based on this data, you have to find out what is the total traffic at the completion of the your project. So that would be P into 1 plus R to the power n plus 10, and you have to design this road section for 10 years. So as the total completion would be taken as 3 years, so your n would be 3, R is your growth rate, so that is 8%, that is 8 divided by 100, and P is the last traffic count. So that is given as 1200. So your total vehicles or ADT is found out to be 3260 vehicles per day. Now, using this, you have to find out what is the total which curve you have to follow. So, in this regard, you have to follow this curve, and you see in the curve there are different these curves are given, and these curves are basically, that is A, B, C, D, E, F, G, that are basically based on the different traffic conditions. So you can see from your data that your total traffic over here is 3260 vehicles per day. So 3260 vehicles per day. So your design curve F should be followed, because F is corresponding to a vehicle number of 1500 to 4500. So you have to follow your design curve F. So based on this, your severe value is 4%. So your severe value is 4%. So you have to find out at which point it intersects. So it will intersect the design curve at this point, and again you have to draw one line to find out what is the total depth of the pavement. So you can find out the total depth of the pavement is like 55 centimeter. So basically that is the total uh, depth of the pavement. Okay, that is the total depth of the pavement. So if you have to find out, or if the total number of vehicles are given, in that case you have to use this curve. And if there is no data is available, in that case you can use that curve. So in that way you can find out what is the total thickness of the pavement. So your total thickness of the pavement is coming around 55 centimeter. Okay, so total thickness of the pavement is 55 centimeter. Now you have to design the different layers. So how you design the different layers? Now compute the thickness of compacted soil. The design curve D is again used for CPR value 7%. Why 7%? See here, another data is given that over the subgrade one compacted sandy soil with 7% severe value is given. So if you use that severe value, 7% severe value, for the same curve, you have to find out what is the total thickness of the pavement. So again you have to find out. So again your curve is F, and now your severe value is 7%. So based on this 7%, you have to find out what is the total thickness. So from this you can find out that your total thickness is like 40 centimeter. Okay, so that is your 40 centimeter, and previously it was 55 centimeter. So your total thickness of the compacted subgrade would be 55 minus 40, that is 15 centimeter or 150 millimeter. So that is given. See, here you can find out that total thickness is 40 centimeter, and previously it was 55 centimeter. So your total thickness of the compacted subgrade would be only 15 centimeter. Now again you have to design for the sub-base course. So in the sub-base course, what is given? Poorly graded gravel with 20% severe value. So again you have to go to the severe curve, and again your curve would be F. Now this value is 20%. So you have to find out what is the severe value, what is the total thickness corresponding to 20% of the test result. Just a minute. So in that case, your CPR value is given as 20% for the sub-base course. So you have to find out that corresponding to 20% where it intersects. So it will intersect over here like 22 or 25 centimeter. So like that you have to find out what is the total thickness based on the 20% CPR value of the sub-base course. So similarly, from the design curve, you have to draw this and it is found to be 20 centimeter or 22 centimeter. So your total thickness of your that is sub-base course is 19 centimeter. So how you get this that 19 centimeter? So initially it was 40 centimeter. After that you get 21 centimeter. So 40 minus 21. So you get the total thickness of this layer. Okay, so after that another layer is there, that is well graded gravel with 95% CPR value. So if you are taking that well graded gravel with 95% CPR value for the base course, in that case again you have to go to the chart and find out where is the 95% CPR value, and according to this 95% CPR value, that is 95% CPR value, you have to again find out at which point it will intersect. Okay, at which point it will intersect. So it will intersect like here. So in that case your total thickness from the curve is this one, that is again a additional of 8 centimeter between a surfacing course would be used. So initially that was 21 centimeter minus 8 centimeter. So your well graded gravel of 13 centimeter should be used as a base course. So this is the total thickness of the pavement, and these are the thickness of the different layers. So this way you have to design a flexible pavement. So we have discussed about the flexible pavement design. Now we have to design the rigid pavement. So basically rigid pavements are the pavements where flexural strength would be there and it is made up of your concrete or PCC, plain cement concrete, and sometimes reinforcement could also be provided. So in the rigid pavement there are different parameters, and in this case the load carrying capacity is mainly due to the high rigidity or high modulus of elasticity of the slab, and that is called your slab action. So HM Westergaard is considered the pioneer in providing the rational treatment of the rigid pavement. So basically the rigid pavement design, therefore we will use different formulas which will together terms as Westergaard equations. So in the rigid pavement design, one important parameter is modulus of separate reaction. So generally this modulus of separate reaction is found out by plate load test. So therefore plate load test in the rigid pavement design is very important. So Westergaard considered the rigid pavement slab as a thin elastic plate resting on a soil substrate which is assumed as a dense liquid. So he assumed that your soil substrate is a liquid portion, that is a dense liquid, and over this your rigid pavement, a thin layer of elastic material is suspended, and that is basically a rigid pavement. And based on this assumption, he formulated different formulas to find out the rigid pavement design parameters. Now, the upward reaction is assumed to be proportional to the deflection. So, based on this assumption, Westergaard defined a modulus of substrate reaction K in kg per centimeter cube given by K equal to P by delta, where delta is the displacement level taken as 0.125 centimeter and P is the pressure sustained by the rigid plate of 75 centimeter dia at a deflection of 0.125 centimeter. So in the plate load test, there are different diameter plates which we use. So this P value is the pressure sustained for the 75 centimeter diameter plates and at a deflection of 0.125 centimeter. So basically in the test, in the plate load test, that total your displacement would be 0.5 centimeter and that would be implied at a rate of 0.125 centimeter per minute. So based on this, you have to find out what is the total subgrade reaction. Total subgrade reaction means how that subgrade is reacting. So another parameter is relative stiffness of slab to subgrade. So what is this relative stiffness? Okay, relative stiffness as per the terms is there. It is defined as a stiffness which is relative to something else. So what is this? So a certain degree of resistance to the slab deflection is offered by the subgrade. So as the your rigid pavement is resting over the soil subgrade, so certain type of deflection is offered by the subgrade itself. Now this subgrade deformation is same as the slab deflection. So how the slab is deflect, similarly the subgrade is also deformed. Hence the slab deflection is a direct measurement of the magnitude of the subgrade pressure. So from the subgrade pressure, as the subgrade pressure increases, deflection will be more. As the pressure decreases, therefore the deflection would be lesser. So therefore it is called that the slab deflection is direct measurement of the magnitude of the subgrade pressure. Now, the pressure deformation characteristic of the rigid pavement leads to Westergaard to define the term radius of relative stiffness L in centimeter, and it is given as by this equation. Okay, so as your subgrade deflection is related to your subgrade, therefore the stiffness provided by the your subgrade is a function of the your subgrade reactions. Okay, so therefore this idea of relative stiffness is found out, and this relative stiffness is given by E into H cube divided by 12k 1 minus mu square, where E is the modulus of the elasticity of the cement concrete in kg per centimeter square. Mu is the Poisson ratio and H is the slab thickness in centimeter and K is the modulus of subgrade reaction. Okay, now another thing is there, that is critical load position. So basically, in the rigid pavement, suppose this is your rigid pavement that is like a plate or that is like a slab. There are different critical positions where load would be maximum or where load would be critical. So basically these are called critical positions. So these critical positions are generally that corner, that edge, these corners and the interior loading. Okay, so these are the critical positions of the load. So since the pavement slab has finite length and width, either the character or the intensity of the just a minute. So there are three typical locations, namely the interior, the edge, and the corner. These are the three important locations where your load would be maximum. So where different conditions of the slab continuity exist, and these locations are termed as critical load position. So your critical position is that in the interior portion, each portion and corner portion of a slab. Now another term is there that is called equivalent radius of resisting section. So when the interior point is loaded, only a small area of the pavement is resisting the bending moment of the plate. So Westergaard gives a relative for equivalent radius of the resisting sections in centimeter as this is the formula. Okay, so if the thickness is lesser than 1.724 centimeter, in that case you have to use this formula 1.6 s square plus h square minus 0.7675 h, or that would be a, where a is the radius of the wheel load distributed over that area. Now there are different type of stresses which will be imposed on the rigid pavement. So first one is window stresses as per the Westergaard stress equations. So these are the stress equation. Okay, where H is the slab thickness in centimeter, P is the wheel load in the kg, and A is the radius of the wheel load distribution in centimeter. Wheel load distribution in centimeter means suppose that is the slab and load is applied over there, and if it is provided distributed like that, in that case what is the total radius of this portion. And this three equation is for stresses interior, stress at edge and stress at corner regions. Now, another important parameter in the rigid pavement is temperature stresses. So, generally, temperature stresses will be higher in the rigid pavement, and temperature stresses are developed in cement concrete pavement due to the variations in the slab temperature during different seasons and during different period of the day. So therefore, there are two type of causes. One is daily variation resulting in a temperature gradient across the thickness of the slab, and seasonal variation resulting in overall change in the slab temperature. So these are the two conditions. Now the former results in warping stress and the latter results in frictional stress. So warping stress, that is warping up. So why warping stress is generated? Warping stresses are generated because of the daily variations of the temperature. Now, warping stress at the interior edge and corner region denoted as sigma Ti, sigma Te and sigma Tc in kg per centimeter square respectively and given by this equation. These are the temperature stresses or warping stresses at interior, at edge and at corner, where E is the modulus of elasticity of the concrete in kg per centimeter square, and it is as 3 to 10 to the power 5, and your Et, that is epsilon T, is the thermal coefficient of the concrete per degree Celsius, that is 1 into 10 to the power minus 7. T is the temperature difference between the top and the bottom of the slab. Cx and Cy are the coefficient based on Lx divided by L, that is the length your length in the x-axis divided by the your length, that one, relative stiffness of the slab to subgrade. So basically what happens during the daytime, your top portions of the slab got heated, but the bottom portion would be lesser temperature, of less temperature, and because of this the top fiber of the slab got extended but the bottom portions remain same. Therefore slab would be warp up like that. So here what happens, because of this tension would be on the top portions but the compression would be at the bottom portion, and because of this warping stress is generated, and during the night season, night time, basically opposite action happens. So during the night time what happens, whatever temperature was at the top portion then gradually transferred to the bottom portion. Therefore the bottom portion got heated but the top portion, because it is in direct touch with the environment, it got cooled down. So there would be a reverse stress positions, that is compression would be at the top portions and tension would be at the bottom portion. So that is the reason behind why warping stresses are generated. Now another thing is frictional stresses. The frictional stresses sigma f in kg per centimeter is given as this equation. So why frictional stresses are generated? See, suppose this is the slab and beneath this your soil subgrade is there. So during the winter season it got contracted, and during the summer season it got expanded. Okay, so because of this contraction and expansion occurs, and the soil subgrade basically resists this action. And because of this resistance, some frictional stresses would be generated at the junction between the subgrade and your slab layer. So therefore, for this reason, frictional stresses are generated. Now these are the cumulative effect of stresses during the different season. So generally summer midday, the critical stresses for each region is given as this one. and winter midday, that is the main equations, and in the midnight these are the main equations for the combination of stresses.